In this lecture, we will go over model selection of covariate relationships to make inference about biological hypotheses. Many of the mark recapture models in this course were developed around research questions for wild populations. So, keeping in the spirit of population biology, we always want to ask why we are fitting a model, so that we can explain the results in terms of biological hypotheses. As mentioned earlier, we will follow the scientific method, and in this course we will focus on developing alternative hypotheses and predictions, designing experiments, analyzing data, and evaluating hypotheses by comparing predictions to data. And by going through this process, we will be in better position to formulate research questions in the future. A hypothesis is a testable statement that proposes a possible explanation for the research question, and a prediction is the outcome you would observe if your hypothesis were supported, often written in the form of if-then statements. If my hypothesis is true, then this is what I will observe. Here is an example of hypotheses and predictions for an additive model for the effects of age, time, and body condition on survival. The goal is to connect modeled covariates to biological hypotheses. Start with writing down hypotheses for each covariate or group effect, and then use the predictions to tell a biological story about what the results will say, and this will be the basis of the biological explanation. Make sure you are clear about what the covariate or group effect is measuring. You may have to do this for each parameter, including capture probability. One of the objectives in model selection is to build models with and without the covariate or hypothesis of interest. One approach is to build all combinations of the additive covariate models, as was done for survival here. However, if we also have multiple covariates for capture, all combinations can result in running a large number of models. Sometimes we want to use sequential model selection to first figure out what is affecting capture probabilities, and then use the most parsimonious capture probability model to evaluate survival. We can use model selection results to provide strength of evidence for hypotheses. For example, there was nearly equal support for the best model with age and body condition in comparison with the second best model with only age. So a delta AICC of 0.64 is fairly even. The best model with age and body condition was 4 times more plausible than the third best model with the additional effect of year, and this is depicted by the evidence ratio, which is the ratio between the AIC weights for Model 1 and Model 3. Next, we can use the beta parameters or regression coefficients on the Logit scale to provide evidence for the predictions. According to predictions we made before running the models, survival from the best model was greater for adults than subadults. The 95% confidence interval excluded 0, indicating a large and precise effect size. Here, the beta parameters and confidence intervals provide statistical support for the predictions. Then we can use the real parameters on the probability scale to demonstrate the effects on survival. Graphing the real parameters at mean covariate values for body condition showed survival was greater for adults than subadults. The first graph was generated for real parameters of the age class groups using the interactive graphics feature in MARC. The second graph was generated by exporting the real parameters to a file and then using ggplot in R. If you are more comfortable working in Excel, you can export the real parameters to a file and then create a custom graph in Excel. It is important to always represent either the standard error or confidence interval in the graphs. In addition, always present a caption that indicates what quantity is being graphed and what the error bars represent. In terms of body condition, the covariate effect was opposite the predictions. Survival decreased with increasing body weight, as shown by the negative sign on the beta parameter. However, the 95% confidence interval covered 0, indicating a small and imprecise effect size. Because model selection indicated nearly equal support for the model with and without body weight, we have two options for making conclusions. One, we can say the confidence interval narrowly covered 0, indicating a marginal effect size that may be measurable with a larger sample size, or the principle of parsimony suggests making inference from the second best model without the effect of body condition. The simpler explanation may be more conservative, and you might choose the second explanation when the covariate relationship was opposite the prediction. Here, the first set of graphs were generated using the individual covariate plot feature of ProgramMark. The second graph was generated using ggplot in R as shown in the lab. Feel free to generate custom plots in Excel, but it is sometimes fiddly to include the confidence intervals for continuous covariates. Use the method of graphing you are most comfortable with. You may need to do a bit more labeling if you use Mark for the graphs.